All right, so far we've gotten pretty good at analyzing circuits by combining resistors in series and parallel. It's a great toolkit, but here's the thing. It has its limits. A lot of real-world circuits just aren't that simple. When you run into a complex, multi-loop network, those methods completely fall apart. So today, we're going to gear up with two fundamental principles that let us tackle any DC circuit you can throw at us, no matter how complicated it looks.
Here's the game plan. We'll start by seeing exactly why our old series parallel tricks fail us. Then, we'll dive into the two brilliant rules from Gustav Kirchhoff that are our solution. We'll lay out a step-by-step strategy for using them, then put it to the test on a tough multi-loop circuit. And finally, we'll see how these rules pop up in the real world, like with power sources and measurement tools.
So what does one of these unsolvable circuits actually look like? Let's take a look at the kind of challenge we're up against.
Check this out. This is a classic multi-loop circuit. See those points where 3 or more wires meet? Those are called junctions. And if you try to simplify this thing, you're going to have a bad time pretty fast. For example, look at that middle resistor, R2. Is it in series with anything?
Nope.
Is it in parallel with anything? Not really. There's no way to boil this network down to a single equivalent resistance. Our old methods are stuck.
So that brings us to the big question, right? If we can't simplify it, how on earth do we figure out the current flowing through each part of the circuit or the voltage across each component? We need a more powerful, more fundamental approach.
And that approach is built on two incredibly elegant but powerful rules. And these aren't just some clever tricks somebody made up. They are direct, undeniable consequences of two of the most fundamental laws in physics, the conservation of electric charge and the conservation of energy.
Okay, our first tool is the junction rule. This is really just conservation of charge dressed up for circuits. Think about it. At any junction, at any one of those nodes, charge can't just be created out of thin air, and it can't just vanish. It's like plumbing. The amount of water flowing into an intersection of pipes has to equal the amount flowing out. Same deal here. The total current flowing into a junction must be exactly equal to the total current flowing out.
And this is a perfect illustration. You've got all these different currents meeting at one point. The law of charge conservation basically says what goes in must come out. So the sum of all the currents flowing in, I1, I2, I4, and I5, has to perfectly balance the sum of the currents flowing out, which are I3 and I6. It's that simple, and it gives us our first type of equation.
Our second tool is the loop rule, and this one is all about the conservation of energy. Imagine you're a little charge taking a round trip, a complete lap, around any closed loop in a circuit. Because the electric field is conservative, by the time you get back to your starting point, your net change in energy has to be zero. You're right back where you started. So any potential you gain from things like batteries has to be completely used up or dropped by components like resistors along that same loop.
This graph is a fantastic way to visualize what's happening. You start at some point, and boom, the battery gives you a big jump up in electric potential. Then, as you move through the resistors, that potential energy gets converted into heat, so you see these drops in potential. By the time you complete the loop and get back to where you began, the total drops across the resistors have perfectly canceled out the gain from the battery. The net change is zero. You end up exactly where you started, potential-wise.
Okay, so we've got our two rules. Now the key is to turn them into a foolproof, systematic strategy that we can use to solve any DC circuit they throw at us.
And here it is. This 5-step procedure is our recipe. First, just label key points. Second, and this is important, find your junctions and just guess a direction for the current in each branch. Don't worry about getting it right. If you guess wrong, the math will just spit out a negative sign later to tell you it goes the other way. It's self-correcting. Third, pick your loops. Just make sure every single component is in at least one of them. Finally, you just apply the rules, junction rule, loop rule, and you'll generate a beautiful system of equations you can solve.
Now, the one place people get tripped up is getting the signs right when applying the loop rule. This diagram is your best friend. Burn it into your brain. When you trace a loop and go across a resistor in the same direction as your assumed current, the potential drops, so you write down negative IR. If you go against the current, it's a gain, so it's positive IR. For a battery, going from the short line to the long line, negative to positive, is a gain. The other way is a drop. Getting these conventions right is absolutely critical.
All right, enough talk. Let's put this whole strategy into action. We're going to take a circuit, set up all the equations from scratch, and actually solve for the currents.
Okay, here's our target. We need to find the 3 unknown currents, I1, I2, and I3. You can see we've already labeled our junctions B and E,
And we've drawn arrows for our assumed current directions. We've also picked two loops to analyze, the one on the left, ABEFA, and the one on the right, EBCDE. Together, these two loops cover every single component in the circuit, which is exactly what we need. First up, the junction rule. This is usually the easiest part. Let's look at junction B. Based on our arrows, we have current I1 flowing in and currents I2 and I3 flowing out. Conservation of charge says what comes in must go out. So, I1 has to equal I2 plus I3. Boom, that's our first equation. Easy. Now for the loop rule. Let's trace the left loop, ABFEA, going clockwise. Starting from A, we cross resistor R1 in the same direction as I1. So that's a potential drop of negative I1 R1. Then we cross R2 in the direction of I2, another drop, negative I2 R2. Then we go through the battery V1 from the negative to the positive terminal. That's a potential gain, so plus V1. We're back where we started, so the sum of all those changes has to be 0. And there's equation number 2. For our third and final equation, let's trace the right loop, EBCD, again going clockwise. Now, starting from E, we cross resistor R2, but notice we're going against our arrow for I2. That means it's a potential gain, so we write positive I2 R2. Then we cross R3 and R4 in the same direction as I3, so those are both drops, negative I3 R3 and negative I3 R4. Finally, we cross battery V2 from positive to negative, which is another drop. The sum of all that equals 0, and we have our complete system. And here it is, all cleaned up. We have a system of 3 independent linear equations for our 3 unknown currents. At this point, the physics is done. We've successfully translated the physical reality of the circuit into a solvable mathematical problem. The rest is just turning the algebraic crank. So you go ahead and solve that system. You can use substitution or matrices, whatever you like, and this is what you get. I1 is 2 amps, I2 is negative 2 amps, and I3 is 4 amps. Wait a minute, hold on. A negative current? What does that even mean? Does that mean we made a mistake? Not at all. This is actually a really common result, and it's telling us something important about what's really happening in the circuit. A negative sign is the math's way of telling us, hey, you guessed the direction wrong. That's it. The magnitude, 2 amps, is correct. The negative sign just means the conventional current in that middle branch is actually flowing in the opposite direction of the arrow we drew. It's flowing upwards, from junction E to junction B. The method automatically corrects our initial guess. It's pretty elegant.
So as you can see, these rules are incredibly powerful for solving complex networks. But they also give us the fundamental principles we need to understand other practical things, like how to combine batteries or how our lab equipment is designed to work properly.
For example, take combining batteries. When you put them in series, the loop rule tells you that their voltages add up because you gain potential across each one as you go around the loop. And when they're in parallel, the loop rule applied to just the loop containing the 2 batteries tells you that their terminal voltages have to be almost identical. Then the junction rule tells you their currents add together to power the circuit.
The rules also explain exactly how our measurement meters work. An ammeter measures current, so you have to break the circuit and put it in series so the current flows through it. And for it not to change the very current it's trying to measure, it must have a very, very low internal resistance. A voltmeter, on the other hand, measures potential difference across something, so you connect it in parallel. To work right, it needs a huge internal resistance so that almost no current takes a detour through the meter itself.
So Kirchhoff's rules give us this beautifully complete and robust framework for any DC circuit we can imagine, all because they're built on the bedrock of conservation of energy and charge. But that leads to a really interesting question. These rules work in a model where we assume the circuit is small and things happen instantly. At what point do they start to fail? When you get to extremely high-frequency AC circuits, or down to the nanoscale where quantum effects kick in, where do these beautifully reliable classical rules finally begin to break down?